Today we will look at the electrical circuits. I have here a small simulator from FET. It's a university in the United States, and they're doing great simulation that we will do together. So what we're going to look into today, we're going to see what is a series circuit, a parallel circuit, and see what happens when we have different quantities of loads in our circuit, but also what happens to the energy of the electrons and how many or how fast they go. So here, this is our simulation. So as you can see, I have here one battery, I have here one switch, and I have here three branches. Now, if you look as a whole, this, we could say, well, nothing is connected, so nothing is changing. So it's hard to know if it's a parallel circuit or a series circuit. So first of all, we're going to see if we can close some switches to see what we have. So if we go here, we have connected this switch, and you see, how come there's no lights that are on yet? Because I have not close these switches. So if I close this switch right here, we have here a flow of electrons going through what we call a series circuit. There's only one loop through which the electrons are going. Keeping in mind that if I open this, we have here a small energy cell. This is the positive end, and this is the negative end. So when I close the switch, the electrons that are close to the positive end gets attracted, and then you end up with a flow of electrons. This flow of electrons allows me to turn on this bulb right here. Now, keep in mind that if we have in this, so how much energy do we have in this energy cell? So here we have a tool that we called a voltmeter. The voltmeter, if you can see, I have it right here. And if you want, I can even give you the link if some of you want to practice at home. Because if you want to practice at home, it's always fun to do so, especially if we don't have equipment. So here I have a voltmeter. And in order to know how much energy is in the source, I'm going to put my two bits here. So here it says that I have 9 volt. We can actually change, if I click here, we can actually change how much energy we have in that energy cell. So here, if I have only 5 volt, look at how much energy comes out of the bulb. But what happens if I put it to 9, to 20, or to 120? But as you can see, the more I have, the more I have light here, that means that we need more electrons with more energy to go through. So I'm going to keep it at 9. I think that's a good number of volts. Perfect. If I have electrons going through this circuit, which is called a series circuit, okay, let's see, can I turn this away? Nope, that's good. Perfect. If I go and check how much energy is being used in the bulb. So if I disconnect it, you see the voltmeter is now off. Let's see if I can bring it up so you can see. So it is off. If you are here at the energy, at the battery here, because we have 9 volts, we have 9 volt. It is connected in parallel because I want to know what is the difference in energy of the electrons between the electrons coming in, gaining energy here in the battery before it comes out. 9 volts is being accumulated. Now, if you go to the bulb right here and I disconnect, let's see, I disconnect, oops, where is it? There you go. So I disconnected the voltmeter. I have no number. And if I put it here, I now have 9 volt. So this 9 volt means that the light here is produced through 9 volts. So electrons are coming in, gathering enough energy to have 9 volts, will go to the bulb and will drop or give 9 volt of energy. Then the electrons with less energy, will go back to the battery, get more energy, and then we have here what we call a series circuit. If I open this one and I close this one, I have another series circuit, but this because there's only one loop through which the electrons are moving. If I open this one and I close this one, this is also a series circuit because there's only one way to go through. Good. Now, what's interesting, if I close this one, you can see here that I have 9 volt. Now, if I close this switch right here, I have now what I called a parallel circuit. Because when the electrons are coming this way, when they reach here, they have two options. They can either take this way or go to the other branch. So 2 branches means that it is what we call a parallel circuit. And if I close this one here as well, electrons have 3 ways to go through. Now, how does the energy interact with the bulbs? As you can see, this bulb here is the brightest. When you have 2 bulbs, it's less bright. And here, when you have 3 bulbs, this is the least bright bulbs. Why is that? So let's see with the connector if we can learn something. So if I connect on my battery here, we know we have 9 volt. That means that we have all the electrons. Oops, the switch is closed. Let's see, let's see what's happening here. I need a switch right here. This way, and okay, so what's happening here? Okay, we'll have to a bit dismantle, but that's all working nicely. There we go. So we have 9 volts at this bulb here because every electrons going on this branch have one bulb to drop all their energy. Now, what would happen if here I go for the 2 volts? The 2, let's see. There we go. If I go for the electrons going from before the 2 bulbs and after the 2 bulbs, you notice here that I have 9 volts because the 9 volts that we get here will be divided in the 2 parts right here. And if I was to look at how much energy is given to each of the bulbs, I have 4.5 here and I have 4.5 here. So here, this is an example. If you go to school from home here, let's say you have 1 class. By the time you go back home, you have given the energy for 1 class. However, if in the morning you leave and you have 2 classes in the morning before lunch, then you have more or less to divide into your energy so that you can actually be able to perform well here. And if you have here 3 bulbs, and I go from before the 3 bulbs all the way to after the 3 bulbs, 9 volts of energy are being used. But if I am to check only one of them, you could see that I have only 3 volts here. So that means electrons going this way will drop 3 volts here, will drop 3 volts here, will drop 3 volts here before they go back to the battery. Now, bulbs, what's interesting, they're called a load, but also they are in the same family of resistors. Resistors, the key point here is to just slow down electrons. So I'll give you an example. If I cut this bulb right here and I take it away, let's open this and this. What would happen if I was to connect, so open the switch here, if I was to connect this one right here and this one. So here we have the electrons that are going to those 2 bulbs. What would happen if I close the switch here? So here the electrons have a choice to go on this line or to this one here where they're slowed down by the fact that they have to give energy to the bulb. Having a choice between going through the bulbs where they're slowed down, they would actually go through the wire that have no resistors. Consequence, the electrons go here, gets energy, goes around, more energy, and then your battery is causing an issue. And that is a problem right there. Let's see how many volts we would have if you have a battery like this. You have 9 volts, and here you could see it's not even registering it is a battery that is not working. Perfect. So that's something that we've learned so far. Let's see if we can do something fun. So what else did we do? We did this one, this one, this one. Okay, let's add a switch right here. Perfect. Let's cut this one here and this. No, let's put a bulb right here. Perfect. And this one turns on. This one turns on. Okay, perfect. So here I have my 2 and my 3 right here. Keeping in mind that if I am to increase this one to 16, for example, then we all see that all the lights are more bright. And if I check here, if I have one bulb, I have 16 volt. If I have 2 bulbs, you've got 8 volts for each of them. So 8 plus 8 gives us 16. And if I have 3 bulbs here, I have 5.33 volts. Why? Because 5.3 plus 5.3 plus 5.3 will give us 15.99 or about 16 volts. So here we are dividing how it is. If I go to 24, let's see right there, you could see that now each of the bulbs here have 8 volts. So here they are sharing their energy to make sure that it's working. But at the same time, you could see that it's slowing down the electrons so that there's a transfer from energy from the electrons to energy, the heat energy and light energy from the bulb. So this is the voltage right here. Now let's see if I can add to this. So I'm going to put the voltmeter right here. And let's see what happens if we are looking at, let's see how we're going to do this. Because I want to show you what happens. Oh, okay, that's beautiful. So when you have an ammeter, you can actually take an ammeter and connect it. But instead of this one, I'm going to use this beauty here because as we are using here, we'll be able to see how many electrons are going through a circuit. Now, the current, so the voltage here we have is the energy in volt for the electrons we have. The current is actually how many electrons are going through one place per second. So here we can see that we have 1.3 amps going this way. If I open the switch, no electrons are going through, right? So yeah, so no electrons are going through. We have 0 amp. We close the switch. We have 1 amp right here. If we get the other one here and we have 2 bulbs, we no longer have 1 amp, but we have 0.5 amp. So let's double check. So here, let's do this. So through 1 bulb, we have 1 amp. If you have here 2 bulbs, we have 0.5 because they're slowing down here through the resistance of these bulbs and they're not as bright. So each of the electrons have the same energy, but we have less electrons going through. And if you have 3, you have 0.33. The reason for that, we have here 3 bulbs, each of them requiring energy. So here we have all the electrons that are being slowed down. But what's interesting here is that if I have 0.3 and here I have 0.5, see how this is moving faster than this branch and this branch. And if I bring it here, I end up with 0.83. 0.83 is 0.5 plus 0.3. So as you can see, when you have a parallel circuit, what happens here is that you may be in a situation where the more branches you have in your parallel circuit, the more amps you end up with. And the issue with that is that the more amps we have, the more dangerous it can be. So here, if you remember, we had 1 amp here. So 1 amp plus 0.5 plus 0.33, we end up with 1.83 amps this way. So this is what we get right here. Interestingly enough, there's a calculations we can have between current and the voltage and the resistance, which is how these bulbs are slowing down the electrons. But that will be another video that we'll be making. So we've talked about current, we've talked about voltage. Let's see here if I increase the voltage on my source right here. So from 10, I'm going to go to 15. As you can see, we have brighter lights, but at the same time, there's more energy for the electrons, but there's also more electrons that can go through. And that is why we end up with lights that are getting brighter and brighter. So in order to have 26 volts here, knowing that we have these bulbs, there's a ratio with how things are going. So here we have 4.77. The issue though is sometimes if you say, well, let's keep on adding, on adding, on adding, on adding. The issue though is that if you keep adding how many volts you need, but also how much current you have, you end up with a source that cannot be able to sustain that, even in reality. So here, let's see if I can. So here it's good all the way to about 14.85. Perfect. If you go in your home and you go into the breaker box, you'll notice that there are what we call breakers. I don't have them here because they're at home, at school at this time. But when you have breakers, it's there to protect the circuits in your house. That means that the more electrons that are moving through, with the more energy we need to save our homes. So the current can be used for that. But often, if you look at breakers, the limit is 15. So if it happens there's more than 15, we have, let's see, we have little fuse. Would it work? Let's see if we can make it work. I think that would be fun. I've never tried the fuse before. So we're going to cut this. We're going to connect those. So the goal of, oh, that's exciting. So it's way too big. I'm going to do this one. I need to repair it. Perfect. So if I have here 4 2 volts, we have electrons going through. We have a current of 0.35, which is great. However, if you are increasing how many amps they are, we can protect a circuit with what we call a fuse. So here I have a fuse that has 4 amp for safety. So if I go here and increase my voltage, I can be working at 15 volt, but I'm at 2.44 amps. That's beautiful. If I go to 3.45, 47, it is great, but as soon as I get above 4, it breaks down. Perfect. So that's something to look into. Now, in my class, my students are always saying, is our equipment very safe? We have a fuse in the power sources. Okay, I need to bring this a bit down. Perfect. We have fuses in our power boxes that are very, very sensitive. And I think it's 0.1 amp. The reason for that is we can do some work, but if we go too high, then it breaks down and we can be safe for students. But in a real house, when you are looking at, so I'm going to take this away. If you're in a house and you have 120 volts running through your house, that means that you need to make sure that you have safety precautions. And these are things I wanted to share with you. It's an initial video. I'm going to show that one to my class this week, and hopefully they will appreciate that as well.